Hi friends, welcome to our channel. So in this video, we are going to look at today's daily challenge problem, problem 3042. Here we are going to give a solution based on the trie data structure, but I want to do a different treatment if you compare with the official solution. So the official solution actually uses two tries. Actually, that's not necessary. So here, basically, we have a list of words. So we want to find the number of index pairs. So like ig, I is less than j, such that so this word I is both a prefix and a suffix of word g, right? So if you look at the example 1, you find that a actually this first one contributes 3 pairs, 0, 1, 0, 2, and 0, 3. And here, this one gives another pair. This is the index pair 1 and 2, right? So this is example 1. So similarly, you can look at example 2. So look, example 2. So this one, PA and PA is a pair, 0 and 1. And also 2 and 3, similar as the first pair, right? So here, this one is longer, so it cannot contribute any pair. So here, this is an easy problem because of the problem size given by the first two constraints. But we don't want to use brute force. So before we implement the solution, let me first give you some overall view of the solution we are going to explain here. So here, I'm going to use a single trie data structure, but I want to encode the count information for the prefix and suffix simultaneously. So there are two key points. The first one is that in the trie, we are going to save both prefix and suffix information and also the count information. So as you can see here, this will be embodied by the trie node definition and the insert and search method. So secondly, I'm going to reverse iterate the word list. So this way, actually, we use reversely build the trie, and then if we look at the index, and then we can look at the trie formed by the index words with larger indices, and to see how many pairs this one can contribute to. So overall, you will get a space time complexity here, like O n by m, and the space complexity O of m. M is the maximum length of the words. That's actually, this will be very ideal. So without further ado, let's do some implementation. First, I'm going to implement a node class. So this node is going to serve as a trie node, right? So so it's going to compute two pieces of information. One is children, so self children. And in the standard trie, so here typically you will have is the end of a word, but here I'm going to strengthen that. I'm going to say is the possible end, so it's 0. So this count, for example, if you insert this one, it's going to say a k like this, and AA, and then you're going to set the possible end attributes to be 1. It means, there's a 1 with both a as in prefix and a as suffix, or you can do this some other case, but you will see this, right? So this is the trie node. Then with this node, we are going to build a trie data structure. For the trie data structure, it's very standard, right? So we have init, so self. So we will have a root node. So it's going to be a node originally, right? Right. Notice that for this node, it has this is the node object. It has two attributes. One is the children tries, and the other is the this count information. So this is that's it. Now let's look at the the two methods insert. So we're going to insert a word, right? And let me first pause that. And also I'm going to do a search, right? So that's self and word. So also I'll use a pass. And then what we want to do, actually the overall structure will be like this. So let's first postpone the implementation of the insert and the search. So let's first write the overall code. Yep. So here we have a result variable. That's what we want to return, right? And then we construct a trie as a trie node, and then we reverse iterate over the list. So basically, for I in range n-1, -1, -1, this -1 is the end, because this range will end before this -1, so we have 0. So this is the step size. Each time is -1 means decreasing. So then we have the current word is words I, right? And then we're going to do this. So we search how many pairs this word contributes. In other words, this is the I will be corresponding to the starting index of possible pairs, and this result will be some words with this current word as both prefix and suffix. So this will be try search, and the search will do something and also give us the count, and then after that we do insert. So we get the so in other words, after each looking at each word, we first check if the current word can form valid pairs with the larger index. If not, then we build the try up to the current index and then iterate for before or decrease the I. So then we're going to return the result. So that's the overall code structure. So hopefully you get the overall idea. So now let's look at the insert. So for typical try, it's very easy to get the insert, or you have another typical methods like is prefix or is word. So here I'm going to adapt to this problem. So let's do the search. You can also compare what's the difference of this insert with the typical insert. Because when we do an implementation of method, we want this method to adapt to our use cases. So that's also demonstrate the flexibility of the data structure, right? So first we have a current, so it's a self root, and then we are going to iterate over the word. So for I, let me write like this: m is the length of this. Okay, let's just do for I in range length of the word. So this each word of length cm, it contributes m chains or m prefix suffix pair. So then the prefix will be word words. So here let's see for I. So yeah, for it would be word I, and the suffix will be word. So the length, right? So the length of the word -1 minus I, right? So if I equals 0, so this is the first one and this is the last one. If I equals 1, this will be the second one, and this one will be second to last, right? So we get the prefix and suffix. And then what we are going to do, so we are going to check this prefix suffix. If this guy not in current children. So notice that this is a dictionary. So the dictionary will have keys and will have values. It will be something like this: pre, sub, and node, try node, right? So this is what we want. So if this does not in this, we can set current, because current is a try node, right? So we can access this children attributes. We set the pre and suffix and to be a new try node, right? So let's see. Try. So I guess this will be much better. So now what we want to do, then we're going to, because currently we look at this one, then we're going to set the current to be actually this one, right? So you can simplify this 3 lines using the dictionary get method, but that's in order to make it clear, we write like this. And then because the pre and the current is the end, so in the process we are going to do this: the current and then the post ends. So we're going to increment by 1. So you will notice why we can have the count information in the node, right? So that's actually the insert method. For the insert, we don't have any specific return. So now let's look at the search method. So when we do the search, we search if the word in it, and also we get the count, right? So we can do self root. So that's the current level, right? You can imagine it's like a binary tree, right? Then we have this current one. We are going to check or for downwards along a certain path. Then for I in range length of the word, then we are going to look at the prefix. It will be word I, and suffix will be word length word, then -1 minus I, right? Then we are going to check if this prefix and suffix is not in current children. In other words, there's no word in the current trie such that this current word given by this argument is both a prefix and a suffix. Then we just return 0. Otherwise, we can reset like in this method, right? So we can actually copy this line. Right, and then finally, so if after the for loop you haven't got anything returned, it means there are some words in the current trie data structure such that the current word given by the argument is both a prefix and a suffix. As we have this possible end count, so we can return this one. Return current possible ends. So this actually encodes a lot of information. And then we have this one, we have this, let me overview the trial data structure. So first we have a node class. So this is a single node. You can think of the binary tree node, right? Or make a comparison. And then here we have a trie class, right? You can think of this as a binary tree, or just a compare. So then we have the root is a trie node, and is a node. And then we do this, right? And then we can do this. This is a very standard. But here, I guess due to the definition of the node here, it enables us to do the search, search if both prefix and suffix are prefix and suffix respectively. And then it also gives us the count, right? And then in the main function or the problem logic, we initialize a result. This is what we want to return. And then we have this trie data structure. Initially, you can understand that it's empty, right? Empty trie. And then we iterate in the backward fashion. And then for each word at index I, so first we check if the current index I or the forms valid pair. In other words, if the word here form is both a prefix and suffix of the later words. So once we get this one, we can increment the count. So if this guy returns 0, it means the current word is not both a prefix and a suffix of later words. Otherwise, you get the count, right? And then you can, then we can update the trie. We can insert the current word to the trie, and then you get the final result. With that said, I guess we are in a position to test this solution. Let me first, so here, try and have pause and let's see, current. Let's see, current This current is a children of this one. Let me see what so we should have this node, right? So here, here, I guess here I made a mistake. So it should be a node. Now let's look at it. Yeah, it passes all the cases. Let me first check if it can pass, right? Yeah, it passes all the cases. So now what we want to do is we do some print to test for this one, right? We know when we look at this one, it's going to give us 1. And then if we look at this one, it's going to give us 3 more. Let's do this. Print f string entering I, right? Word is given by this one. Words I. So actually we can add the print here anyway. So we have this word and result state. So now let's see. Exiting. Say the word and also the result, right? Print. So let's look at this first example. You can see here, when you look at this word, because this last word, you should have 0 and 0. And if you look at this one, you also should have 0 and 0. Then if you look at this one, you are going to get, before you enter this, you get 0. After you exit this one, index 1, you are going to have result 1. And then if you look at this one, it will contribute 3 pairs. Then if you, when you just enter, its result is 1. And after you exit, it's 4. And the 4 is what we want to return. So with that said, I guess we finished the coding part. So in this, I guess you can try some other problems in LeetCode to practice the trie data structure. You can start from some simple problems, where you just need to implement the insert is prefix or not, is word or not, and then you can then try some problem with more complex logic. That would be actually a lot of fun. With that said, I guess that's it. Thank you for watching.